Welcome back. This is section 3.2, starting on week 3. This week we're going to go ahead and start covering variance and standard deviation, right? One of my favorite parts of the class. All right. There are no discussions this week, so you have nothing to worry about for this week regarding discussions. Discussion 2 will begin next week. So let's jump right into it, right? So for variance, right, the formula for variance is going to require 3 important parts, right? It's going to be n, right? And it's going to be the number of values that we have in our data. The sum of x squared, right? That's going to be all the values you have squared and then adding them up. And the last value, right, would be the sum of x. Pretty much just summing all your x values, right? So let's go ahead and see its applications, right? Let's go ahead and see its applications. So, time spent in rush hour traffic. A sample of 12 drivers shows the time that they spent in minutes stopped in rush hour traffic on a specific snowy day last winter. Find the range, variance, and standard deviation. Since we've done range already, right, I'll go ahead and let you find the range. If range isn't necessary for finding variance, right, so let's go ahead and find n, right? N is going to be the number of values in my data. So this is going to be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? So it's going to be 12. Now, let's go ahead and find the sum of my x values, right? Let's sum of my x values. So that's going to be the bottom part, right? And let me just go ahead and make sure that was 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah, it was 12. Oh, and that's given too, right? 12 drivers shown. So that let's go ahead and sum my x values, right? So this is going to be 45 plus 47 plus 46 plus, and I'm going to add all these values all the way up to 59, right? Let's go ahead and add up those values and see what it gives us. And I got 711, right? The next part is going to be squaring each value and then adding it up. So in other words, this is going to be 45 squared plus 47 squared plus, right? I'm going to square each one and then add them all the way up to 59 squared. Now let's see what that gives us. And I get 43,167. Okay. So let's go ahead and make this a little bit smaller. And I'm going to go ahead and plug those values. I'm going to go ahead and plug these values into the variance formula, right? The formula for variance is s squared is equal to n, which is 12, times the sum of the x values that were squared, right? So that's going to be 43,167 minus the sum of the x values, which was 711, and I'm going to square those. And remember, these two values are going to be very different, right? These values are always different, so always keep an eye out for that. Divided by 12 times 12 minus 1, right? Let's go ahead and see what that gives us. And yes, by all means, this is I really want you to use your calculator here, right? So definitely take advantage of that, right? Let's go ahead and see here. We got 12 times 43167 minus 711 squared divided by 12 times 11. And this gives me let's see, let's go ahead and do 2 decimals, right? So this is going to be 2 decimal places. This is going to be 94.57. 94.57, right? 94.57. And this here would be your variance, right? This here would be your variance. If you want to go ahead and find your standard deviation, you go ahead and solve for s squared, right? So how do you get s by itself, right? How would you get s by itself, right? I would go ahead and take the square root to both sides. So in other words, once you find your variance, all you need to do is pretty much take the square root to find your standard deviation, right? And let's go ahead and see what that gives us. The square root of 94.57 will give me 9.72. So that there would be my standard deviation, right? Let's go ahead and apply that on another example. But on this example, we're going to go ahead and apply to Excel, right? So let's go ahead and get that started. So we're going to go ahead and apply what we know, but in Excel, right? So the first thing here I'm going to want to find is going to be my variance, right? And here I'm going to stay my standard deviation, right? So we're going to be using the same values we were using before, right? So the great thing about Excel, right? You can go ahead and use it to check your work, right? So let's just say you went ahead and did all this hard work, right? And just, you know, you just want to go ahead and make sure you have the correct value. I would recommend exporting this to Excel, right? The formula is going to be equal. And for variance, it's going to be VAR, right? VAR. I'm going to open this and I'm going to highlight all these values, right? I'm going to highlight all these values. I'm going to close this. And there we go, 94.5. We said 2 decimal places, right? So let's go ahead and get that to 2 decimal places. So 94.57. To find your standard deviation, sure, you can go ahead and find the square root of 94.57, or you can just make the equal sign, right? And for standard deviation, it's going to be STDEV, right? I'm going to open parentheses. I'm going to highlight my cells, close, and there we go. 9.72, right? 9.72. Let's go ahead and try this on another example, right? Let's go ahead and go back. Right? The cigarette taxes, the increases in cents in cigarette taxes for 14 states in a 6-month period are, well, this is going to be information for 14 states. So I know my n is going to be 14, right? My sum of my x values, right, is going to be 51 plus 60 plus all the way to 31, right? And then the sum of those values squared is going to be 51 squared plus 60 squared plus 31 squared. And let's see what that gives us, right? Let's go ahead and plug this into our calculator. And the values I got are, it's going to be 505 for my sum of x. And for my sum of x values that were squared is, I got 20,599, right? Now let's go ahead and bring that formula over, right? Let's go ahead and bring this over. I'm going to use that as a reference. And yes, here we are. So my variance is going to be 14 times 205.99 minus 505 squared over 14 times 14 minus 1. And let's see what that gives us. And for my variance to 2 decimals, I get 183.30, right? So this here would be my variance. And for my standard deviation, let's go ahead and take the square root of that, right? 183.30. That's going to be, my standard deviation is 13.54. Awesome. Let's go ahead and move on to the next example. So our next example is going to be finding the variance and standard deviation, but with a frequency distribution table, right? Our formulas are going to be about the same, right? But it's going to be dealing with midpoint, right? Pretty similar to the previous homework sections that we had, right? And we said once we have our class boundaries and frequency, I'm going to want to go ahead and expand this table, right? And we're going to go ahead and find my midpoint, right? And do we remember how to find our midpoint? To find our midpoint, I'll go ahead and add for the specific class that I'm referring to, right? I'm going to add the lower boundary and the upper boundary and divide it by 2, right? So this 7.5 plus 12.5, right, divided by 2, that's going to give me 10, right? For the second class, 12.5 plus 17.5 divided by 2, that's going to give me 15, right? It's going to be 20, right? And we know this is going to give me 25, and 30. There we go. And then we had mentioned that it's going to be my frequency times my midpoint, right? So this column will give me 40, right? The second column, right, 7 times 15, that's going to give me 105. 15 times 20, that's going to give me 300. That's going to give me 125. That's going to give me 150, right? And then our last column, right, is going to be my frequency multiplied with my x midpoint, but the x midpoint has to be squared, right? So in other words, what I'm doing for this one is going to be 4 times 10 squared, right? 10 squared gives me 100, and 100 times 4 gives me 400. Right? For the second column, I'm going to be doing 7 times 15 squared. This is going to be 1575. And we'll go ahead and do that for all these sections, for all these classes. And it gives me these following values, which is 6,000, 3,125, and 4,500. And now let's go ahead and sum these values, right? Let's go ahead and sum all these values. Let's go ahead and sum up this column. And let's go ahead and sum up this column, right? So that's going to give me 40 plus 105 plus 300 plus 125 plus 150. This gives me 720, right? The last column gives me 5 plus 12,800, right? 12,800, right? And what is my n, right? How would I find my n, right? How would I find my n value? Will it be counting how many classes I have? Or will it be the sum of my frequencies? Correctly, it's going to be the sum of my frequencies. So it's going to be 4 plus 7 plus 15 plus 5 plus 5, which is going to give me 36. And now I can go ahead and apply this to this formula, right? Now I have everything I need. Let's go ahead and plug everything in. All right. So my variance is going to be 36 times 12,800 minus 720 squared over 36 times 35. And let's see what that gives us. And I actually found out I had gone off, right? If you caught that early, that's all. That's great. Right here, this should be 15,600, right? Right. So this here is going to make a big difference. And how would you know, right? So whenever I was summing these up, I caught that mistake, and it's all right, right? So one way to know is that your your variance and your standard deviation must be greater than 0, right? They must be positive. You can't have like a negative square root, right? So that there was the indicator that this value here was too small, leading me to believe that my computations, right, that number was incorrect. So let's go ahead and plug that in now, right? So for my variance here, my variance is 34.29, right? 34.29 would be my variance. And to find my standard deviation, right, this is going to be 34.29 taking the square root, meaning that my standard deviation is going to be 5.86. 5.86. So this here is how you find the variance and standard deviation with a frequency distribution table. Now let's go ahead and move on to the next example. So now we're going to be talking about getting the coefficient of variation, right? CVAR, right? So the coefficient of variation is denoted by CVAR. It is the standard deviation divided by the mean and then multiplied by 100 to get a percentage. That is it. And that information will be given to you, right? Like for this example. The mean of the waiting times in an emergency room is 83 minutes with a standard deviation of 10.1 minutes for people who are admitted for additional treatment. So I know that for the people admitted for additional treatment, I know the standard deviation to be 10.1, and I know the mean, right? The average is 83 minutes. That's going to be for one case. Then I am also told the waiting time for patients who are discharged after receiving treatment is 110 minutes with a standard deviation of 16.3 minutes. Which times are more variable, right? So here I'm going to go ahead and find these formulas for both of these, right? So for the CVAR for discharge, right? CVAR for discharge, right? So that's going to go ahead and be, is it the top information or is it my bottom information, right? It's going to be my bottom information. Right? And let's go ahead and find our standard deviation, which is 16.3 divided by the mean, which is 110, multiplied by 100, right? So this here, 16.3 divided by 110, right? This here is going to give me, let's go ahead and give 4 decimal places, right? This is going to give me 0.1482, right? So now I'm going to go ahead and multiply that by 100, and this is going to be 14.82%, right? And to find that which time is more variable, it just means which has the highest percentage, right? So this is going to be for discharge. Now let's find CVAR for additional treatment, right? This here is going to be 10.1 divided by 83 times 100, right? And then 10.1 divided by 83, that's going to give me 0.1217 times 100. This is going to be 12.17%, right? So the one with the highest CVAR, right, is going to be my discharge. for this next example, it's going to be a very useful theorem, right? It's going to be Chebyshev's theorem, right? Chebyshev. And Chebyshev's theorem is the proportion of values from a data set that will fall within k standard deviations of the mean with at least, and here's the formula, 1 minus 1 over k squared, where k is the number greater than 1, right? K is not necessarily an integer. You could get a decimal value, right? So, right, let's go ahead and start, right? Using Chebyshev's theorem, solve these problems for a distribution with a mean of 71, right? Right, that's going to be important, and a standard deviation of 11. Round k to at least 2 decimal places, and final answers to at least 1 decimal place if needed, right? So that means my k is going to be 2 decimals, and my final answer is going to be just 1 decimal place will be fine, right? Right. So the sub question, right? Part A is going to be at least what percentage of the values, right, will fall between 38 and 104, right? So how we start here is going to be step 1, right? Step 1. Let's go ahead and stretch out this way. Now let's go ahead and a little bit this way. There we go. Right. So step 1 is going to be, you're going to want the large value, and you're going to subtract that from the mean that was given to you, right? And specifically, I'm referring to 38 here as a small value and 104 as the large value, right? So I'm going to go ahead and get 104 minus the mean, right? And the mean was given, that is 71. And I'm going to go ahead and compute that difference, right? That's going to be 104 minus 71. That difference is going to be 33. And you're going to want to hold on to 33, right? Because that is what I'm going to need to find my k value, right? So k, right? Oh, it's right here. K is going to be the difference that you found divided by the standard deviation that was given, right? So that means k is 33 divided by 11, right? 33 divided by 11, which is what? 3, right? So my k equals 3, all right? This is going to be my second step. And last but not least is going to be plugging it into that theorem, right? Plugging it into Chebyshev's theorem. And that is simplifying 1 minus 1 over k squared, all right? Well, that is 1 minus 1 over 3 squared, which is 1 minus 1 over 9. And what do we need to do to go ahead and add these two fractions, right? What do they both need? Well, they both need the same common denominator, right? So 1 I know is the same thing as 1 over 1. So this means I need to multiply this n by 9 and that n by 9 as well, giving me 9 over 9 minus 1 over 9, right? Which is 8 over 9. Let's go ahead and compute that. 8 divided by 9, that's going to give me, and we said 2 decimal places, right? So that's going to give me 0.89, right? 89. If you're asked to give a percentage, right? So we're going to go ahead and multiply that by 100, right? That's going to be 0.89 times 100, and that's going to give me 89%. Right? Let's go ahead and go ahead and do another one, right? Let's go ahead and do another one. And here I want to know at least what percentage of the values would fall between 43 and 99. So we said what we wanted to go ahead and do is get the difference, right? Let's go ahead and get the difference. And that's going to be the largest value, which is going to be 99, minus my mean, which is 71, right? And I'll call this the difference step, right? The difference step. 99 minus 71, right? That gives me 28. And now I can apply that to formula 2, right? Formula 2 said it's k is equal to the difference that I just found divided by the standard deviation. So that is going to be 28 divided by 11, right? 28 divided by 11. That's going to give me a decimal, right? And we said 2 decimal places, right? So this is going to be 2.55. 2.55, right? We'll go ahead and do 2.55. So let's go ahead and plug that in to Chebyshev's theorem, which is 1 minus 1 over k squared. So this is 1 minus 1 over 2.55 squared, right? This is 1 minus 1 over 2.55 squared. That gives me 6.5025. And yes, for parts like this where it's 1 minus 1 over 6.5025, please use your calculator, right? I don't want you taking too long simplifying this, right? So please definitely take advantage of your calculator, right? And in calculator, how I would plug this in would be 1 minus parentheses 1 divided by 6.5025, and I get, right, we wanted this last value up to 1 decimal, right? But we'll keep it to 2, right? This is going to be 0.85, right? And if I multiply this by 100, right, this is going to be 85%. 85%, and this was 89%. And this here is Chebyshev's theorem. So for this next example, right, continuing Chebyshev's theorem, you're going to be given the other types of values, right? So for this specific question, you're going to want to know those bounds, right? From what to what, all right? That's what we're going to have to find, the large value and the small value, right? And the question here tells us time spent online. Americans spend an average of 4 hours per day online. If the standard deviation is 39 minutes, find the range in which 88.89% of the data will lie. Use Chebyshev's theorem, right? So one really thing you need to remember here, right, whenever we're dealing with math, is that you want all your units the same, right? So specifically looking at standard deviation and the mean, right, my average, I want this to be the same unit, right? So if my standard deviation is 39 minutes, right, I'm going to went ahead and convert 4 hours, right, to minutes, right? And 4 times 60, that gives me 240 minutes. So let's remember that. Let's be on the lookout for that, right? So what we're going to want to do now is solve for k, pretty much, right? So here, right, we're already given the answer, right? We're giving the percentage, right? But now we want to find those lower and upper bounds, right? So I know with Chebyshev, right, it is 1 minus 1 over k squared is equal to a percentage, right? It's equal to a percentage, right? So in other words, what I want to go ahead and do, right? Let's go ahead and leave that up there, right? Because it's going to be very useful. Let's go and leave that. We'll leave it on this corner, right? So let me go ahead and apply that, right? Let me go ahead and apply that so I can find k. That's going to be 1 minus 1 over k squared is equal to 88.89%, right? But one thing we had mentioned before was that I don't want to handle numbers whenever they're in percentage, right? So to get rid of the percentage, you would divide them by 100. So this is 1 minus 1 over k squared is equal to 0.8889, right? And now here I solve for k, right? Now here I'm going to want to solve for k, right? One thing we may want to do is let me subtract 1 to both sides. I'm going to take that and I'm going to take that away, right? So this here is going to give me negative 1 over k squared is equal to, right, is equal to 0.8889 minus 1, that gives me negative 0.1111, right? Now, I want to go ahead and multiply both sides by negative 1, right? I want to multiply both sides by negative 1 so I can get rid of the negative, right? So I can get rid of the negative. So this is going to be 1 over k squared is equal to 0.1111, right? What I would then want to do here is, I know any number is itself is just the same thing as divided by 1, right? Like 5 is the same thing as 5 divided by 1. 7 is the same thing as 7 divided by 1. And the same thing applies with decimals, right, and negative values. So I'm going to go ahead and do that. The reason I want to go ahead and do that is because I want to get rid of these fractions, right? I'm going to go ahead and do cross multiplication, right? And I can only do that whenever I have a fraction equals a fraction. So this here is 1 times 1 is going to give me 1 is equal to 0.1111 times k squared. That is going to be 0.1111 times k squared. All right. You're trying to solve for k squared, and this value is being multiplied by the variable, right? And if you're trying to solve for k and something's multiplying by it, you're going to want to divide both sides by it, right? I'm going to do that to both sides. I'm going to go ahead and write it here nicely. So this cancels out, letting me know that k squared is equal to 1 divided by 0.1111. Right? And what is that? What is 0 divided by, what is 1 divided by that decimal? 1 divided by that decimal is going to give me pretty much 9, right? This is pretty much 9. It's 9.00090009. So that's pretty much 9, right? This is going to be 9. And then what do I do to go ahead and solve for that value, right? I would go ahead here and apply the square roots to both sides, right? These cancels out, letting me know that k is equal to 3. Haha. I like that. I'm going to want to use this. So to find my large value, right? The large value is going to be the mean added to the multiplication of k times s, with s being my standard deviation, right? And to find my lower value, it's going to be pretty similar. It's just going to be the mean minus k multiplied by the standard deviation. So let's go ahead and find large. Large is going to be my mean, which was given, that was 240, plus k, which we found to be 3, times standard deviation, which is 39. Right? And what does that give me? That gives me 240 plus 3 times 39. This gives me 357, right? Let's go ahead and find small. That is going to be 240 minus 3 times 39, right? This is going to be giving me 123. So that means that the range of values right? The range of values there we go. The range of values is between 123 and 357, and that there would be my final answer. Right? So this is the other Chebyshev's theorem question you may be asked. And here we are. Right? We're going to be referring to the empirical normal rule, right? The empirical normal rule. And what this pretty much states is, if you have a symmetrical bell-shaped curve, right, with the mean in the middle, right, applying the mean and adding it to 1 times a standard deviation, right, would move it forward that way, and subtracting it one way would be this way, right? It'll be to the left, right? And if you notice here, right, going 1 standard deviation forward and 1 standard deviation backwards, it lines me up here. Lines me up here, right? And this means all this information between there, it's 68% of the values that you have, right? That 68% are contained there, right? If I apply the same thing, right? If I go 2 standard deviations to the right and 2 standard deviations to the left, right? I'm going to be about here. Well, not about, exactly there, right? And if I go in reverse, it's going to be there. And this is going to account for 95% of your data, right? And I'm sure you already know, if you were to go forward by 3 standard deviations from your mean and backwards, right, that's going to account for 99.7%, right? So this table here is very, very useful, right? It's very, very useful because you'll be asked to find data with specific values, and these percentages that we should be familiar with are going to be 99.7, 95, and 68%. Right. So let's go ahead and remember that we know how that's being applied, right? We know how that's being applied. Okay. So let's go ahead and apply this to a problem, right? The national average for mathematics on a standardized test was 503. Okay, so I already know that and whenever you're reading these, you really want to go ahead and write down what you know, right? Write down what you're given, right? So I'm already told that the mean, right, that my average is 503. Suppose that the distribution of scores was approximately bell-shaped curve, right? And that the standard deviation was approximately 48, right? Within what boundaries would you expect 99.7% of the scores to fall? What percent of the scores would be above 599, right? 599. Okay. So one of the things I want to go ahead and first do is going to go ahead and find, let me bring this chart here, right? 99.7%, right? 99.7%. When I go here, 99%, that means I'm going to use this portion, right, which is the mean plus 3 times the standard deviation, and I'm going to use that back portion as well, right? I'm going to use those two. So I'm going to use these two formulas, right? So I'm going to use my mean minus 3 times my standard deviation, and my mean plus 3 times my standard deviation, right? And this here, right, my mean was 503 minus 3 times my standard deviation, which is 48. And that there gives me 503 minus 3 times 48. This gives me 359. And this here is going to be 503 plus 3 times 48. Right, this gives me 647. So that means 99.7% of the standardized math tests scores all right, so that means that 99.7% of the standardized math test scores will fall between 359 and 647, all right? Let me go ahead and make this a little bit smaller. Right, so whenever you're giving these, give me 1 second here. Right, whenever you're giving that percentage, right, that's going to be a clicker right there. Whenever you see 99.7%, 95%, or 68, that's how you know you're going to be leaning this way, right, for these formulas, right? Now, let's go ahead and go on to the next part. What percentage of what percentages what percentage what percentage of scores will be above 599? Can really see that there, right? So whenever we see this, we're going to be leaning towards Chebyshev's theorem, right? Because we're talking about what percentage of scores would be above a value, right? Will be above 599, right? Will be above 599. So we're going to go ahead and find the difference, right? We're going to go ahead and find the difference, right? I'm going to find the difference. It's when my difference here is going to be 599, right? Because that's my focus value, right? It's not going to be 647, right? It's going to be the focus value that was given to me, right? It's going to be above 599, which is that's my large value here, minus my mean, right? Which is 503. And this here gives me 96, right? And what I'm looking for is my K value, right? I'm looking for that K value because that's gonna tell me a lot. Then my 2, we said to find K. This is the difference divided by the standard deviation, which is 96 divided by 48. Oh, that's nice. That gives me 2, right? That gives me 2. Right, let's go ahead and get that the chart. This one right here. Right, and if it's 2 standard deviations, that means 599 will be right there, right? And everything is engulfed with these 2 points, right? So you have to ask yourself, if all of this here, right? And the reason I'm focusing on there is because it gave me that 2, right? It gave me that K value. Right? It gave me that right there. That's what I just found, that K equals 2 value. So I know everything here accounts for 95% of it, right? All of this here is 95% of it, where this is 599. How much is out of it? How much is outside of it? Well, that's only going to be your full 100% minus your 95%, right? Which is going to leave you with 5%, right? And let's be careful here. The question asked, let's go back to the question, right? What percentage of the scores would be above 599, right? Above 599. So this is 5% is above 599 and below another score, right? To the left, right? But since this is symmetrical, this means all of this here would be what? What's half of 5? This here would be 2.5%, right? And this other half here, this would also be 2.5%. So we really need to be careful what they're asking, right? You would approach this the same way with the Chebyshev, but you would stop at that K value, locate, right? Locate what percentage is it locked in. It's locked in between, which we stated is 95, subtracted by 100, and then divide by 2. Right? So this here would be 2.5%. So that's how much would be above it, right? That is the percentage of scores that would be above 599. It'll be 2.5%. Okay, so going back to the empirical graph, right? Let me clean this up. We pretty much see, and this is going to be very important whenever we're finding values later. For this graph, right? For this symmetrical empirical graph, the standard deviation is usually at most your 3 and -3, right? It stays, it's not -3, right? But it stays within that range, right? And that, with that range between -3 and 3, we can tell a lot from the symmetry of the graph, right? And this is going to lead us to the final part of this section, which is going to be Pearson's coefficient of skewness, right? this is going to be the formula, right? 3 times the mean minus the median, all of it divided by the standard deviation, right? And what this pretty much is it's going to tell us the skewness of the graph, right? Is it negative skewed, positively skewed, or is it symmetrical, right? To get from this is if PC, right, Pearson's coefficient is 0, it's symmetrical, right? If the value that you get is positive, it's positively skewed. If and how you would probably thought already, if it's negative, it's negatively skewed, right? And then one of these problems is just pretty much a plug and chug, right? So this is going to be, let's do the first example, A. The PC is going to be 3 times the median. I'm sorry, 3 times the mean, which is 9, minus the median, which is 10, divided by my standard deviation. All right, and let's see what that gives us. It's going to be 3 times the negative 1, right, divided by 4. This is going to be negative 0.75, all right? It's negative, right? So this is going to be negatively skewed, all right? Let's do another example, all right? My PC is going to be 3 times 43 minus 45 all over 3, all right? And have you have already guessed, the sign is really dependent on the on the values of your mean and your median, all right? So this is going to be 3 times negative 2 divided by 3, right? These cancel out, leaving me with negative 2. That also is negatively skewed, all right? And this is all I would ask you for this coming section, right? Regarding the PC of skewness. So this is all I have for today for this section for 3.2. The focus, the emphasis, right, on this section is very heavy on variance and standard deviation, specifically when you're dealing with values like this, right? When you have them all laid out, as well as a frequency distribution table, and specifically, right, what's going to taper into the next following sections is going to be Chebyshev's theorem, right, and as well as the empirical rule, right. And like I said, make a note of these values, right? These values, the three standard deviations going forward and backward would be 95%. If it's just one forward and one backward, it would account for 68% of your data, and 3 standard deviations forward and backward would account for 99.7% of your data, right? If, let's just say, right, you accounted for all of this data here, this is 68%, and you want to know how much is over here only, right? You only want to know what's above that value, about that first standard deviation. You said you would go ahead and get 100% and subtract it by that 68%, right? Which will give you a 32%, right? So a 32 is going to account for the back end and the forward end, right? But if you only want to know the back end, or if you only want to know for the forward end, you would divide that by 2, meaning that anything above this value, that first standard deviation, would be 16%. Like I said, that's all I have for you today for this section. Good luck studying. Happy studying. Thank you for your time.